welcome everyone in this seminar. So today we have a speaker, Prolay Chanda, and to introduce him, Prolay completed his masters from IIT Madras. Then he joined Indian Institute of Astrophysics. Then after that he moved to University of Illinois Chicago where he is currently as a PhD student. So, thank you, Prolay, for accepting our invitation. And for you, this is an not very convenient hour, we believe, but we have to manage somehow for this time gap. So, our speaker, Prolay, will be talking today about decoupling of asymmetric dark matter in the early matter-dominated universe. So, please, on behalf of everyone, I welcome you to this meeting. Over to you, Prolay.
For the invitation, and please feel free to stop me whenever I don't make sense. And today I'm going to talk about a decoupling picture of asymmetric dark matter during an early period of matter domination. And as Shura already introduced, I am a PhD student and at University of Illinois Chicago, and my doctoral advisor is Professor James Alwyn. And before I start the talk, I like to outline what I'm going to talk about. It is segmented into three topics. So first I will talk about matter-dominated freeze-out of dark matter, and then it will follow with a discussion on asymmetric dark matter, and then I will talk about a SO10 connection to the asymmetric dark matter picture. Now, let's start with matter-dominated freeze-out of dark matter, and the inspiration of that freeze-out during matter domination starts from this very the experimental summary till date, and this picture tells us all the experimental bounds we have performed on a WIM scenario. WIM stands for weakly interacting massive particles, and it is one of the simplest candidate for dark matter, as you can write down. And it is nice because we can do experiments and we can figure out that in which parameter space the dark matter can be found. The WIMP models work such as that for a given dark matter mass, you can define a certain cross section such to match the dark matter radial density as observed today. And the solid circle here, the red circle here, that stands for the classic WIM scenario. And as you can see, the most of the top part of the shaded region is currently ruled out by the current detection, dark matter detection experiments. And at the bottom, there is still a large portion of parameter space where the dark matter can still be found. But we thought that this is a good motivation for look for some alternative scenarios. And this particular picture is taken from the SNOMAS data, the last one. And so here is a summary of the history of the universe. And like after Big Bang nucleosynthesis, there was the cosmological history is mostly well understood and well accepted in the community. But in the beginning of the universe, it is believed that there was an inflation, a sudden expansion of the universe, and following that, to the time of Big Bang nucleosynthesis, the history is not very well known. It is not a single idea is widely accepted. So the most common idea is that the universe remained radiation dominated from the end of inflation till the Big Bang nucleosynthesis. Now we propose an alternative scenario, or we look for an alternative scenario where there was a small chunk of time period where there was a short matter-dominated time period. And why we propose such an alternative scenario? So, because the cosmology is largely dominated by the expansion history. As we know, the universe is expanding, and for the expansion of the universe, we can define a parameter which is called the Hubble parameter, and that grows differently for different history of the cosmology. For example, sorry, when if the universe remained radiation domination, the Hubble parameter grows as T squared, temperature squared, and if there is a non-relativistic matter which dominates the energy density that time, then the Hubble parameter grows as T to the 3 over 2. And if it happens that uh, at a certain time period, a heavy field is decaying, in that time the universe expands as temperature to the fourth, as shown in a classical article by Skerr and Turner. And why it is so important? Because so when we coin the term freeze out, it basically means that the density freezes out. So for any particle spaces, they are interacting with each other. If we look at the early birth, and at the same time the universe is expanding. It is like in a box. If you think that all the particles are colliding with each other and the box itself is expanding. So there will be one point you can imagine that when the expansion rate will be greater than the interaction rate, so that the one particle will never come close to the another particle. So there won't be any annihilations. So after some time, the number density of a given particle species will be frozen out, and this is what we call as freeze out. So roughly this freeze-out condition is given by that the decay rate is roughly equal to the Hubble expansion rate. Now, if we change the cosmic history, the Hubble expansion rate changes, and that essentially gives us more freedom on the annihilation rate. And rate is proportional to the cross section, and cross section is the particle physics for dark matter. So when you change the cosmic history, it also changes the dark matter particle physics. And that's why we are interested to explore the matter-dominated freeze-out scenario. So what is a matter-dominated freeze-out scenario? So here we propose that there is a heavy field which we call as phi, and it starts with some initial density which we will denote as small r. So small r is the fraction of radiation compared to the relative to the total energy density in the thermal bath when the phi field starts to evolve like a matter. And what happens that you can see in the figure that this is the radiation. It starts from here, and here is the phi field. And initially, the energy density of phi field is less than radiation. So we can take initially we can take the factor to be 10 to the minus 2. But what happens with time that with the by the if you solve the Boltzmann equation, and we know in cosmic history, in cosmology, that energy density of both of the radiation and matter will decrease with time, but for radiation it decreases faster. So that means after a time the matter will start dominating the energy density in the thermal bath, and during that time, the thermal bath will be non-relativistic, dominated by the heavy field. And this matter-dominated period, so the junction point here, where the blue line goes up and the red line goes down, basically means the universe becomes matter-like. So the phi field starts to dominate over the radiation, and then this initial flat region, what we can confidently call a matter-dominated phase. Now, this vertical line stands for entropy violation. This EV stands for entropy violation. And what is the entropy violation? So what will happen? The phi field will come into dominating the energy density. then it will dominate for some time, and then eventually it will decay. And as it decays into radiation, into lighter particles. And as you know, in just in thermodynamics, that if it creates new lighter particles, it increases the entropy of the bath. So that means it not actually reheats the universe, but it slows down the process of cooling of the universe. And also that in the Boltzmann equation, we have to take into account for the decay of the phi field. Now we do not consider this scenario. In our analysis, we do not consider this scenario. Mainly because in this particular region, as we can look back here, the Hubble parameter is not matter dominated. It actually goes as temperature to the fourth. Now that also can be an interesting scenario, but that is very different from a matter dominated case. So we restrict our analysis in this flat region, where in the x-axis, this is the logarithm of a scaled time parameter. Now, so as I said, that as the field decays, it will decay into lighter particles. So there will be the entropy will be increased, and also that by the classic article by Skerer and Turner, they showed that this decay into lighter particles doesn't actually increase the temperature of the universe, but only slows down the cooling process. So that is very important, because initially it was believed that as the phi field decay, the temperature will increase for some time, but it happens like it only slows down. And also that this parameter, the time parameter, the temperature parameter T star, this we define as a temperature when the phi field begins to evolve as matter. And TMD here is the temperature when the thermal bath begins to behave as a matter dominated phase. Now these two are different. So T star is roughly equal to the mass of the field. So as the universe cools down, when the temperature is roughly equal to the mass of the field, that is the temperature T star. So T star is essentially of the order of m phi. But TMD is given as T star times this fraction, where R is the fraction of radiation present in the total energy density uh, when T equals to T star. So it is more like an initial condition. For example, if I choose R to be 0.01, that means that when when the temperature of the universe is roughly equal to the mass of the field, that at that time R equals to that 0.01. And so, as I said, that following freeze out, the number of dark matter particles will remain constant, and we define the factor zeta, which is the fraction of the entropy before and after, which is basically the fraction of cube temperature of the decay temperature and the reheat temperature. And when I coin the term reheat temperature again and again, I just want to say that this reheat temperature is very different from the inflationary reheat temperature, where the inflaton decays into radiation. It is just the reheat temperature related to the phi field we propose here. And why this entropy? So what this entropy dilution gives us? So if we see that for a non-relativistic spaces, the Rayleigh density is given by mass times the number density divided by entropy. Now this is important because the density is inversely proportional to the entropy. So if I increase the entropy, that means the density is less for a given particle spaces. So that means we are allowed to overproduce the dark matter during freeze out, and then following the entropy dilution, we can match the current Rayleigh density of dark matter as we see today. And this is nice because in the standard picture, what we have in the standard wind scenario, we have for one dark matter mass, we can have one dark matter cross section or one dark matter coupling. But now we have a third free parameter, which is this dilution factor. So we can allow for smaller annihilation cross sections and then dilute the density produced at freeze out, so to match the energetic density today. And so we can write down the Boltzmann equation for the dark matter, and this equation cannot be exactly solved analytically. So one way to do is we solve it numerically, or we can do it semi-analytically, like with some approximations. So what we do is we expand the thermal average cross section in powers of velocity, and then replace the velocity with temperature, and then we can write sigma v as a sum of some coefficients times x to the minus n, where x is the scale temperature, which is mass over temperature. Now, this expansion can be very naively realized that if you expand the cross section in velocities, you can get terms like v squared, v to the fourth, and so on. And you realize that for an ideal gas, half mv square equals to some temperature. So that means you can replace the v squared with temperature and mass, and then you can expand in terms of temperature and mass. And then we define the Hubble parameter in the following manner. And here, the star, the subscript star represents the time when the phi field starts to evolve like a matter. And you can see, if I substitute for r equals to 1, the Hubble parameter grows as t squared, which is radiation domination. And for r equals to 0, the Hubble parameter goes as t to the 3 over 2, which is matter domination. Now, one of the solution is the classic solution for a semi-analytic solution was done in a classic article by Skerrer and Turner. And so this is the freeze-out temperature considering radiation-dominated thermal bath, and this is the radial density.
Prolay,
Now, two important.
hello.
Yeah,
I have
sorry.
a question
Yeah.
that in your equation, what is that E chi? In your
Uh,
yeah,
E chi.
yeah.
E chi is the center of mass energy of the dark matter particles.
So is this equation dimensionally correct? In the Boltzmann equation, I think is there any energy involved there? Because because
Uh,
n chi goes as t cube and t goes as 1 by m. So, okay, we can later on discuss that. I
yeah,
think
yeah, yeah. We can discuss it. I think I can check because I can
it's
check it.
not correct. I think. Okay, you go on.
Yeah, yeah. Maybe yes. We can talk at in the end. Yeah, I think there can be a type. Um, so can I proceed?
Yeah, yeah, yeah.
Yeah. So yeah. So what I was saying that here is the solution for the freeze out temperature, and here is the solution for the freeze out relic density. Now, two important points are that the freeze out temperature that logarithmically depends on the cross section. So, in a way, it means that for a certain range, for a closer range of cross sections, the freeze out temperature doesn't vary much. That means if you just check that the mass over the freeze out temperature, which we will call later as x subscript f, that is essentially almost a constant value, which typically arises like 25 in a typical WIM parameter space. But also interesting is to see the relic density, that let's say we want to fix the relic density to the current observed relic density of the dark matter. Then for one cross section, we can have one dark matter mass, which the mass dependence comes through the freeze out temperature. So this is important that you take one dark matter mass, let's say you say 10 tera electron volt, and you say what is the coupling I can have? So that will be one single value. It is a one-to-one relation. Now we can do the same solution for the matter-dominated freeze-out, and we will see that the most of the solution remains same, but we now have an extra degree of freedom in terms of zeta. This zeta is the entropy dilution, which gives you the extra degrees of freedom in the sense that now it is not one-to-one correlation between cross-section and mass. For example, for a given dark matter mass, you can choose that there is no entropy dilution, let's say, then I have one single coupling. Now I can change the entropy dilution factor to 10 to the minus 1, 10 to the minus 2, and many others. And for each of those values, I can have different cross-section values. So that means I can now tune the parameter space more freely so that I can see whether I have some parameter space where the dark matter can still be realized considering the current experimental bounds. And so for detailed calculation, please look into these articles. And before further discussions, I would like to discuss some of the consistency conditions. And one of them is that the matter domination has to happen before freeze out and after the matter domination, after the phi field starts evolve like matter. And the next is we don't want to destroy the successes of Big Bang nucleosynthesis, which was roughly given as I think 10 mega electron volt, but we remain conservative, so we choose the reheat temperature to be more than 0.11 giga electron volt, and then we consider that the freeze out of dark matter occurs before the phi decays, and we also consider the scenario where during the freeze out we can neglect the phi decay. So if you remember the plot that I told that if the entropy violation becomes important, then the Hubble parameter grows as t to the fourth instead of t to the 3/2. So we do not consider that region. And of course, for cold dark matter, we choose the consistency condition that the freeze out temperature is less than mass over factor of 3.
Prolay,
Yeah.
this is Surina here.
Yeah.
So why it is called entropy dilution? Because entropy is increasing actually.
Oh, right. I think it is called entropy dilution in a way.
Because the dark matter freeze out density is decreasing.
Diluted by entropy. So I think from that way.
Because sometimes it's misleading because entropy is actually not reducing. Yeah.
Yeah. Right. Yeah. So I think that's how the term was coined, but it is confusing. Yes. Yeah. So then we can write down one of the simplest wind scenario where the dark matter interacts with the standard model through a Higgs portal, and we can write down the following Lagrangian for a scalar dark matter, and we can see that after the symmetry breaking, it takes the following form. Now we can this mass term, the dark matter mass term, is actually have a correction term which depends on the coupling, but what we see in our choice of parameter space that the dark matter mass is mostly equal to the bare mass, so we do not consider this dependence on the coupling. Now, what we expect to see in the case of radiation domination, that there will be a one-to-one correspondence between the mass and the cross section, and this exactly have been produced by Escudero, Berlin, Hooker, and Lin, and so this solid and dashed black line, the black contour, that is fitted such that so in y-axis lambda is the kappa in our notation, and the m phi is actually the mass of dark matter. So it is fitted such a way that we choose such a mass of dark matter and coupling so that the Rayleigh density of dark matter today is exactly 0.12. And all these are experimental bounds. The green one is the background neutrino flow. The xenon and lux are the underground xenon direct detection experiments which look for kinetic rebounds of the dark matter particle if they collide. And the red dashed region here, that is the invisible decay width. So the idea is we collide the standard model particles, and then if the Higgs decay into some channel which cannot be detected, that can be a possible source of dark matter. So that also gives us a experimental bound, and as you can see that most of the parameter space are ruled out because anything above the experimental bounds are ruled out. So only thing is part is allowed is the region around the resonance point. So resonance point means the roughly the mass of the mediator. So for this case, the mediator is the Higgs, and only this region we can find a dark matter candidate. But as you can see that through with the current experimental bounds, this is largely ruled out. But what happens when we change to matter-dominated scenario? That now we can change. So yeah, just I will go back just to remind you that I can relate the entropy dilution factor with the reheat temperature and the T star, right? So that means with different choice of the reheat temperature, I will have different entropy dilution factor. So you can say that if I choose different reheat temperature, in a way, it says different entropy dilution. And with that, we'll see that where I had only one contour, now I can have many contours as I wish, as long as the reheat temperature is more than that PBN temperature. Now we can see that here are the consistency conditions that freeze-out temperature is less than the decay temperature, then it should be less than entropy violation, and if less than reheat. All of these are not ruled out but are not consistent in our theory. So any colored region in this plot are inconsistent in our model. So only consistent region in our model is the white region. And next what we do, we overlay the experimental bounds on it, and we have already discussed neutrino floor, lux and xenon, and this is the indirect detection coming from Fermi, the Fermi lab data. So what Fermi lab data does is that it looks for dark matter annihilations in these dwarf spheroidal galaxies, and they look for, I think, the annihilation channel to bottom quark, and so that gives you some bound, and this is so as you can see that on this right hand side, this white parameter space is can still be realized in our model, like we can still found the dark matter. So when we consider matter domination, we revive the Higgs portal in a sense that with any reheat temperature between, say, below 100 gigaelectron volt, the dark matter can be found. So for the case of radiation domination only allowed region is the resonance point, but if we when we consider matter domination, we have large chunk of parameter space which can still be realized. Only constant remains the neutrino floor here, but as long as you are consistent with other experimental bounds, you can not care about neutrino floor, because for higher dark matter masses, for higher energies, the detection of or the bound of neutrino floor is itself in doubt. But the main point or takeout from here is that just changing the cosmological history, you can revive one of the most classic wind picture model. Next, what we do the same for different dark matter models, particle physics models. Here we consider Fermion dark matter, and on the left we show the matter-dominated scenario, and on the right we show the radiation-dominated scenario. And as you can see, for the Fermion dark matter 2, where only the resonance region is allowed, For the matter-dominated scenario, we again have a large chunk of parameter space when we can still detect the dark matter. And we do the same for the Z portal. To keep things simple, we only consider vector coupling, because if you do not consider the vector and axial coupling to be equal, you can get into technical troubles like anomalies and all. Because our main concern is not to complete the particle physics, but to show that all of these classic models can be revived by changing the history of the cosmology. And with that, we can go move into the next topic, which is asymmetric dark matter. And
can I ask you a question?
Yeah.
So the gray shaded region is your allowed space?
No, the gray shaded region is actually the consistency conditions. So that means that in the gray shaded region, our theory is not consistent. So it is not ruled out, but it just says that whatever our contour and whatever we have done analytically is not valid in that region.
So what is the region here which is which is allowed from neutrino floor as well as from Lux and
So
Chanda?
so it is the this white parameter space on the right, not by the neutrino floor, but by the other experimental bounds.
Okay.
So
Okay.
I do not, like I said, we do not care about neutrino floor much, because for this energy range, especially between 10 to the 3 to 10 to the power 4 gigaelectron volt, the detection of background neutrino is itself in doubt.
But you also have a low mass zone where you are satisfying neutrino floor left side. Why?
Yeah, right.
Yeah.
But this region is wide enough, but the one on the right looks more promising because it is allowed everywhere. So it is more promising in that higher mass region.
Yeah. Okay. Yes.
Yeah. Um, okay. So now I will talk about why we are at all considering asymmetric development. So the main motivation is that the relative density between the dark matter and baryons are of the order of 5, which is in a way of order of 1, right? In the in the all the parameter scale we consider, in that order it is of the order of 1. Now we know that for baryons, the current density is set by the asymmetry. So there was the initial asymmetry, and the symmetric part was annihilated away, and the asymmetry remains today as the current baryon density. And we also know that the baryon, not know, but the most accepted theory is the asymmetry was introduced through a out of equilibrium decay with C and CP violation and the baryon number violation. So this is called the I think Affleck-Dine conditions. So we are interested to this is a good motivation for dark matter also being asymmetric, and we propose a similar scenario where a certain x number is violated, where x is some unknown conserved number in general, like the baryon number, and that causes the initial asymmetry for dark matter, and then the current density of dark matter is set by that asymmetry. And we define the asymmetry similarly as the baryons, just that the difference between dark matter and anti-dark matter, and we divide it by the entropy. And so with that, we can write down the Boltzmann equation again and again, like you have already asked. I will check the dimensions after the talk is over. But the main point is, once we write down the equation, we can substitute for the number density and temperature and rewrite the equation as the abundance as a function of the scale temperature. So x is mass over T. This is what I am calling scale temperature. And plus and minus stands for dark matter and its antiparticle. And lambda n here is a function of mass and sigma n, the cross section. sorry, and G effective here is the standard relativistic degrees of freedom for the case of radiation domination. However, for matter domination, this G effective is a function of R, which is the fraction of radiation in the total energy density when phi starts to evolve as matter. Then the T star, the temperature when phi evolves as matter, and then XF, that is the freeze out condition. And we can again go ahead and do the solution, the semi-analytic solution, and you can see the solution remains exactly the same except for the newly introduced term which is proportional to the asymmetry, so mass time asymmetry. So the idea is to have a similar picture as baryons. You need to have the symmetric part, the first part, to be washed away by effective annihilation. So that the density today is given by the mass times the asymmetry times the dilation factor for the matter dominated case. We can also do a numeric solution of the Boltzmann equation, and this is given here, and this is very interesting because for the same set of parameter space, that is eta is the baryon asymmetry I said here, and the cross section is the Wien cross section, and we choose the matter domination and dark matter mass to be such, and what we see that for the case of radiation domination, the dark matter asymmetry, the dark matter abundance is set by the asymmetry. If you look carefully, for dark matter, the abundance is nearly equal to 10 to the minus 10, and its anti-counterpart is almost annihilated away. So this is the typical asymmetric particle densities, relic density scenario. However, for the same parameter space for matter domination, we have a symmetric scenario. So that means the cross sections were not effective enough to get the symmetric part annihilated away so that they both are comparable in number, the dark matter and anti-dark matter. So the essence of the plot is that whenever you change the cosmological history, it changes your particle physics and your model. Just the change of the expansion history. And next what we do, we again start from the semi-analytic solutions. Again for the detail of the calculations, you can go ahead and look in the article. And we can make a contour plot between the asymmetry and the dark matter mass. So here we assume a model independent approach where the cross section goes as 1 over mass squared. We consider dark matter to be a scalar boson, and we cut off the plot at mass greater than some 25 T star value because beyond that it is not a matter dominated freeze out. Now this plot is very interesting because let's go back to the equations and let's say the symmetric part is annihilated away, right? And when that can happen? When the asymmetry is high enough. So when the asymmetry is high enough, the relic density is simply mass times eta. So that means I increase eta, mass decreases, I increase mass, eta decreases. So this is the plot here, the one-to-one correspondence, when the eta is high enough. However, we see the vertical lines in the below because the asymmetry will be so low that there cannot be effective annihilations to wash out the symmetric part, that the relic density is given by the symmetric part itself, which depends on the cross section, and in a way it depends on the mass itself. So for a given mass you have these vertical lines. And also that you can see from here that the entropy dilution factor is a prefactor, which means that you higher when you choose a smaller entropy dilution, or higher entropy dilution I should say, like 10 to the minus 10 is higher than 10 to the minus 8 in that sense, and then you can go for higher asymmetry. So next I defined, we can define fractional asymmetry, which is basically the fractional dark matter, anti-dark matter compared to the dark matter. And what analytic relation we arrive at is that the fractional asymmetry depends exponentially on the cross section. So it decays exponentially, not decays, it decreases exponentially with the cross section. Now this is math, but you can realize it physically. So higher the fractional asymmetry I have, so when higher I mean 10 to the minus 6 is higher than 10 to the minus 2. So when I have higher fractional asymmetry, then that means I have smaller number of anti-dark matter particles for a certain number of dark matter particles. So the annihilations have to be more effective or more sufficient to produce the relic density observed today. So this can be understood from this plot that if I take higher and higher fractional asymmetry, I have to increase the cross section so that the annihilations are effective enough, so that there are enough annihilations, so that the symmetric part is washed away. And the black solid line is the contour for the radiation dominated scenario. All the colored line are for the matter dominated scenario. Why I have many lines for matter dominated scenario? Because I have an extra degrees of freedom zeta, which depends on T star or eta. It depends on the way you will choose. And with that, I will conclude my discussions on the asymmetric dark matter here, and then I move to a interesting scenario of SO10 connection to asymmetric dark matter. Now, why SO10 is interesting? Because anytime you propose a dark matter model, you have to impose a Z2 symmetry so that the dark matter is stable. Now, most of the cases, what we do that we impose the Z2 symmetry by hand. Now, it would be nice to have a theory which proposes the dark matter particle and also satisfies its stability. Now, if we look back to standard model, what is its group structure? It is SU3, SU2, U1. So basically, its rank is 2 plus 1 plus 1, which is 4, right? So if I consider any model which is beyond the standard model and at least have one rank above, that is 5, let's say, then that can have a symmetry which is outside of the standard model, which will be then broken into a Z2 symmetry and stabilize the dark matter. So one of the such a model can be the grand unified model, which which we consider here. So we consider a SO10 group, and at first it is broken into the intermediate scale, and then the intermediate scale is again broken into the standard model group and a Z2 symmetry. And in our particular example, the one we take from Nagata et al., and they consider the case when the intermediate scale is broken by a 126 dimensional representation of SO10. And our dark matter candidates here are the lightest particle of 16 and 144 representation or a scalar multiplex, and they are, because they are lightest, they will be stable under the Z2 symmetry. So that is the model we consider here. And with that, we consider the right-handed neutrinos, which acquire masses through Yukawa couplings, which is defined here. The small L here is the lepton doublets, and we consider the lightest right-handed neutrino, and if they are long-lived enough, then they can cause the matter domination, which we are talking about till now. So it's like the right-handed neutrino, the lightest one, acquire mass, and then it starts to dominate the energy density, and then it decays. But in between, during that matter dominated phase, this lightest dark matter under the 16 and 144 scalar multiplet will freeze out and produce the dark matter relic density as we observed today. And so we propose a similar Higgs portal scenario as we discussed before, and we consider the electroweak symmetry breaking, and then we reproduce the plots. But now it is different because it has initially the asymmetry, which we represent in terms of the fractional asymmetry, which we take 10 to the minus 2, which means during freeze out, there was one anti-dark matter for every 100 dark matters. And as we can see on the right bottom, in this white parameter space, we can have a very promising dark matter candidate. And the right-handed neutrino will start behaving like a non-relativistic matter at when the temperature is proportional to its mass, which is choose to be 10 to the 10 gigaelectron volt, and then we can calculate the matter domination temperature using this relation. So as you remember, R was initial condition that the initial density in radiation compared to the total density in the path when the right-handed neutrino starts to evolve like a matter. Now, with that, I would like to conclude my talk. And so, first point is that if we consider an early period of matter domination, it will relax the parameter space, and which will revive the classic models through the Higgs and Z portal. And then the dark matter can be asymmetric, just as baryons. Um, it can be. It is a good motivation, and we see that with the idea of asymmetric dark matter, we can still produce a very viable dark matter candidate obeying the current experimental bounds. And then we propose SO10 group to be a promising framework, which can at the same time propose you a dark matter candidate and also can assure its stability through a zero symmetry, and which is very nice because you can then have a UV completion scenario. And with that, I would like to conclude my talk. And thank you very much. And I'll be happy to take some questions now.
Okay, one can unmute oneself and ask questions.
Okay, Sumina here.
Yeah.
So, I have a naive question here. I don't work on that under that much in the particle aspect. So, I know that the classic miracle is kind of gone, no? Because that predicts 10 to the power minus 39 centimeters square cross section.
Yeah, right.
But so, how tuned is your dark matter annihilation cross section to match the Rayleigh density? Is it natural or you have to tune it?
So I won't call it tuning because tuning means you fix a set of parameters. Like you have a very narrow set of parameters which validates the Rayleigh density as observed today. But
Yeah.
on the contrary, what we have here is very different. So let me compare these two plots. So let me take these two plots. So what happens is radiation domination. Let's say I find there is a dark matter particle for 1,000 gigaelectron volts. So for that,
That I understand because you have an extra freedom of entropy,
yeah, right.
entropy dilation. But what I'm saying is, do you have a natural cross section which has other prediction than just matching the Rayleigh density? Because here you are matching the Rayleigh density
Right.
with a broader range of parameters. But how do we know that it is just not an explanation or there is some other prediction in the cross section? Interesting range of cross section in other particle physics.
That I am not aware of if there are other motivations. But I just want to say that there is no fine tuning in this approach.
I got it. Yes, because you have an
yeah. So just that I think the main constraints and consistencies comes from the experimental bounds and cosmological consistency conditions. But from
So
the
with this Higgs portal opening, with this Higgs portal, is there is any other way to predict? Because other than just a dark matter detection, because ultimately you have to pin down that what is the signature of this
Yeah,
particular.
right.
Yeah.
The correct cross section and mass.
Yeah.
So I am not aware of, but in that way, with your question, this matter-dominated picture is more complicated because if there in the case scenario of radiation domination, if I know the dark matter mass, immediately I will know the cross section, which will help me to go to particle physics. Or if I know the from particle physics, I know what is the cross section, I know the dark matter
Yes.
mass.
Yeah.
But for matter domination case, because there is also a cosmological history related to it, we have to know both of the cosmology and the particle physics at the same time to fix all of our parameters.
Yeah.
Okay, I have a question that
Yeah,
as you are considering the entropy dilution, so dark matter mass would be higher than the normal situation because numbers are less
right.
due to dilution, so you need higher mass. So now my question is, can you somehow put some bound or any theoretical constraints on how much entropy can be diluted? Is it related to the read temperature or something? Because you see,
Uh,
if you can infinitely dilute anything, so you would get larger and larger masses. So can you somehow constrain the entropy dilution?
so one thing I can't infinitely decrease the entropy dilution factor because of the Big Bang nucleus synthesis constraint. Because the reheat temperature have to be greater than the Big Bang nucleus synthesis temperature, right? Because otherwise everything is messed up. But coming back to your question, that yes, that in the in between range, that let's say I take one of the viable plot, and between the reheat temperature of 100 to 1 giga electron volt, um, I am not aware of if I can pinpoint such a entropy dilution factor, because I we can do that if we can have something from the particle colliders or experimental bounds. So here the problem is I have three free parameters: the coupling, the mass, and the reheat temperature or the entropy dilution, right?
Hmm.
So I have to know at least one of them to fix the entropy dilution. So for now, we can say at least in our analysis, it is very much free.
Acha. Okay.
Yeah.
So any other questions?
So my question is from the last part of your talk. So
Yeah.
whatever large group you have considered, first of all, I
Yeah.
do not know what are these SO10 guts scale
Yeah. Yeah.
gut theories. So the Lagrangian seems to me as the basic type one seesaw.
Right. The
So
seesaw.
so the neutrino part, 900 neutrino part.
Oh, okay. You mean that one? Okay. Yeah. Right. Because that's what I want to have, right? So, sorry to interrupt you. The main idea, if you look here, so uh, I do not expect you to follow every details like SO10, but the main idea is I follow a framework where the SO10 group is broken down into the standard model and the Z2 symmetry. And the Z2 symmetry only stabilizes the dark matter, so that means everything will look similar as the standard model. So that is expected, right?
So just for the, I mean, motivation of UV completion, so you get to a group which is larger than the rank 4 is okay, right?
Yeah. So the idea is I have standard model which is SU3, SU2, U1. So 2 plus 1 plus 1 plus 4. Now I know that in standard model there is no such a symmetry like all the symmetries we have, that explains the known particles, right? So any new candidate to stabilize it, you need a higher symmetry to be broken. That is the whole idea. It is so forget about this SO10 and all these details. So think about I need a higher symmetry of 4 plus x. I choose x to be 1, which is 5. And it happens that SO10 is of rank of 5. And that extra symmetry is broken down to a Z2 symmetry, which stabilizes the dark matter. That is the idea.
Okay. So you want to generate the Z2 by dynamical braking without even imposing by hand, right?
Yeah, right. So at the same time, I want to propose a dark matter particle, accord its mass, and also stabilize the dark matter. Because otherwise, you just have to impose that you have to write that I consider a dark matter particle which is Z2 invariant. But you do not say why it is Z2 invariant.
Okay. Okay. So here the dark matter candidate is the right-handed neutrino.
No. So let me repeat it again. The right-handed neutrino is the heavy particle species which results into the matter domination, and dark matter is the lightest particle of 16 or 144 scalar multiplex of a SO10 representation. I consider the lightest one because it will be stable under zero symmetry. The 16 and 144 is not relevant here. Just think about that there can be many like particles under a multiplet in a certain group, and the lightest one will be the most stable under the symmetry. So that's why I consider the lightest one.
Okay.
Okay. Thank you.
So,
Yeah.
so any
Hi,
other?
I have a question that is in connection to the Deep's question. So can we get some bound in your xi m chi plane from the S matrix unity? I mean, from the if we use the condition of S matrix unity, the maximum cross section, then can we get some bound in the xi m chi plane?
Okay. Let's talk in a more general manner. So what is S matrix? That is basically particle physics, right?
Yes.
So the point here is, let's go back to the plot. So let's take this plot. So for the radiation dominated scenario, it is much more simpler because what you are saying, I find the particle physics, let's say, and I will know either of the dark matter mass or the coupling. Then my dark matter theory of dark matter is complete. The problem with the matter domination is, though we have the large chunk of parameter space available right now, but only calculating the S matrix will not restrict the zeta. We also have to know either of the mass of the dark matter particle, because now we have 3 degrees of freedom: the coupling, the dark matter mass, and the zeta. Right. So if I can somehow restrict the coupling, if I know the dark matter mass, then only I can say that okay, this particular value is the should be the entropy dimension that time. So in this case, we need to know both of cosmology and particle physics.
Okay.
No, I think
Yeah.
Yes.
I think
Yes.
Shogatoda, what he was talking about, that you have sigma v. Let's say you consider it in a model
In a
independent.
model independent
Yeah,
scenario.
yeah. So
Yeah.
So
yeah, yes,
you have only two parameters, xi and sigma,
and mass
Okay.
and mass.
and
And sigma depends on the mass of the dark matter.
right.
Right.
In the standard framework, sigma only depends on the mass, and rate density there is no explicit dependence on the mass parameters. It depends via sigma, right?
No, it also depends on mass parameter because the freeze out condition depends on the mass.
Yes, the condition of freeze out is roughly independent, right? So
Yeah. So if you see the
yes,
XF,
sorry, just continue.
yeah. Sorry, the XF, this
Mhm.
XF, if you look here, it depends on the mass.
Yes, but the dependence is in a law scale, right? I mean log
Yeah,
of
log
sigma.
scale, but so it depends slightly, but it depends. So I can tell you that the parameter space I'm considering, it varies from something 10 to 50, but that is in case of radiation domination. In matter domination, it will vary even more. But I think let's come back to your question. I think what you are saying is I do not consider a model dependent scenario as such with some mediators, but just write it as kappa square over mass square. Is that what you are saying?
Just write sigma, and you use the sigma from the S matrix unitarity. That is 4 pi by m chi square.
Yeah, 4 pi over m chi square. Then essentially that means that I do not have any hand on the coupling, right?
No, you can vary xi and m chi on only.
Yeah, but what I'm saying, like from the perspective of cross section in general,
Yes,
it
yes.
should have two hands, the coupling strength and the mass. But if you take the zeroth order from the S matrix, which is 4 pi over m chi square, uh, that that we can do, but that is basically you are assuming something, right? Because that assumption is also like fixing a parameter. Yes, then if that is true, if I take the S0 term, then I have the relation between mass and the entropy dilation. But remember that now there is no in a way the cross section is now fixed on the dark matter mass. Like like it only depends on the mass. There is no such thing as the coupling. And in a way, personally, I think the coupling is important. The model dependent approach is important because the coupling strength is what differentiates between other standard model particles.
That's
That's
right.
how it becomes weakly interacting massive particles.
That's right.
Yeah, I mean, whatever you are saying, it is a good suggestion. But I'm just saying, personally, I think it is important to keep that coupling strength hand because that is the whole hierarchy thing in the particle physics of cosmology we are doing, right?
Yes,
So when you
that's
say
right.
weakly interacting, I'm just looking to the weak strength.
So,
Yeah,
yeah, yeah. Thanks for your
yeah,
clarification.
yeah. Sure.
So, is there any other questions? So, if not, let me thank Prolay for your nice talk and time. I know that it's been late there in Illinois. So,
Yeah,
so so thank you. I would not further stretch this seminar.
yeah.
So
And
let me call it a day here and thank you. And can you please send us your presentation via email? Then
yeah,
we can.
yeah, that I can do. And please, any of you, feel free to send questions. Like one of them, you pointed out, the dimensions are not correct.
Yeah,
I'm
yeah.
very
Dimensions are
interested.
not correct. I checked because you see that the dn chi dt
Yeah,
is
yeah,
is m to the power 4, and
yeah,
in the right hand side there is n square, that is m to the power 6, and
yeah.
sigma be m to the power minus 2. So there won't be any e
Right,
factor. So that's a typo, I
right.
guess. Yeah.
I'm very sorry about that.
No, no. Okay,
So
that's
for any
fine.
such questions or like doubts you have, please feel free to email me.
Okay.
And thanks again for inviting me. It was a pleasure from myself.
Okay.
And you all have a nice day.
Okay. Thank you.
Yeah.
Thank you.
See you.
Thank you very much.